Hello everyone, my name is Antoine Desjardins, and today I'll be explaining to you a new algorithm which is called Leaderless Consensus algorithm. It's a Byzantine indulgent leaderless consensus algorithm. So why do we need consensus algorithms? Consensus algorithms are very important for blockchains, smart grids, and etc., which is why we need them to be very performant. So basically a set of processes trying to agree on the same value and make sure that everyone has agreed on said value and they can trust this value. More precisely, a consensus algorithm has to satisfy three properties: validity, which is making sure that the value is valid, for example, that it's a value that comes from one of the participants. Agreement, which is to make sure that everyone agreed on the same value. It's very important. Together, the two properties are safety. Then we have liveness. In liveness, we have termination, which is making sure that the algorithm eventually terminates and everyone eventually decides on the value. When you want to do this in a realistic setting, so with an indulgent algorithm, so when you have, for example, eventually synchronous assumptions, the way you usually do it is you elect a leader, but electing a leader is very problematic. It's very slow. It can cost 10 times overhead over the usual span execution of the algorithm. And it's a single failure point. It's very centralized and it makes the blockchain easy to attack and easy to delay. You just have to attack one single process and you can block everyone if you choose the process right. So if we want to have blockchain that are better and more powerful, we need better algorithms and we need leaderless algorithms. But what does that even mean? We have to define a new notion of leaderless algorithms. And for that, we define a new property, which we call leaderless termination. Leaderless termination implies termination. It means that every correct process terminates even in the presence of leaderless behaviors, or if you want, a sort of leaderless faults. You will have Byzantine processes, for example, and correct processes. But now, with the leaderless fault, we'll have correct processes, which will get interrupted even when you are in the synchronous suffix of the execution. And they will get interrupted for a finite period of time. They will eventually wake up and perform calculations. But in the meantime, as they do not perform any calculations, they do not receive any messages, although they will receive those messages later. And obviously, they do not send any messages. Of course, those processes can switch in between. Some will wake up, some will fall asleep. Maybe all of them, or most of them, will be woken up at some point. But we can never have more than 1/3 of processes which are either Byzantine or correct, but interrupted. You can see it as an execution where you have weak synchrony. So you have synchrony, but you still have some processes behaving in a kind of asynchronous way for a short period of time. So for example, for one round, from one step of calculations, they will not perform anything. They will behave as if they were interrupted, asleep, etc. So now we have to wonder, does such an algorithm exist? And the answer is yes, such an algorithm exists. And we made one. It's called Archipelago. It's a leaderless algorithm. And the fun thing is that Archipelago is compatible with leader-based algorithm. If you make it into an abstract, you can have leader-based algorithms switch to leaderless algorithms like Archipelago if they feel like they are under attack or something like that. Archipelago is actually very promising since we made it optimal in terms of complexity. So time complexity is optimal, resilience is optimal, optimistic termination is optimal, and bits exchange are state-of-the-art, they're competitive with PBFT, for example. Only number of message exchanged in an execution is not state-of-the-art, but what really matters for scalability and throughput and latency is bits exchanged. So we devised several versions of Archipelago. We have Byzantine versions, we have omission fault versions, we have shared memory versions, and message passing versions. We also have with or without authentication. I will try to present to you the simplest way, shared memory and omission fault, so that you can get a high-level idea of how the algorithm works. So basically, we'll have this object, this black box object, which is the adopt commit max object. It takes in input several values, which are the value proposed by various processes, x1, 2, etc. And it will either adopt the maximal value if the values are not all the same. Or if all values are the one and same, then it will commit this value. And what will happen is that each process will have a series of these adopt commit max objects coming one right after the other, each one taking an input, the value, and the adopt or commit that was outputted by the previous object. And eventually, you will have all processes after picking up the max each time, clearing out all values except one, which will be sent by everyone, and everyone will be able to see only the same value from everyone they got a response from and commit said value. So I'm going to make a quick sum up of what we've seen. So we want our algorithms to be good. We want them to be resilient to attack. We want them to scale well, and we don't want them to be performant. If you have a leader election, you cannot be resilient because the leader is a single failure point. You cannot scale well because the leader will have trouble sending many messages to many people if you scale a lot. And this will hinder performance in the long term. It will slow throughput. It's a bottleneck. It's a leader bottleneck. So you need to have a leaderless algorithm. And in order to have this, you need to define a new definition of leaderless because it doesn't exist yet. And we've come up with the definition of leaderless, which can be seen as a property the algorithm has to satisfy, a leaderless termination, can be seen as a type of fault where correct processes can get interrupted even when you have reached the synchronous part of the execution. But you can see it as a type of weak synchrony where even the synchronous part of the execution is not fully synchronous. We have proven that such an algorithm exists because we have made one, which is Archipelago. And we have even been able to optimize it until we have reached a complexity in various regards, which is either optimal or state of the art. And as such, Archipelago is probably the best algorithm out there. And I think it would be a very good application to use it as a backup, if not as the main algorithm for new blockchain systems.